So we'll discuss about velocities and accelerations from different frames of reference. So we'll construct here two frames. This one capital X, Y, Z. This is the ground frame. This one will be the ground frame, and one more frame is the moving frame with small x, y, z, maybe tilted also like this, small x, y, z. This is the moving frame. It may be an accelerating frame also, moving frame. And we will consider a particle T here, particle P whose position vector from this frame, moving frame, will be rho, and from this ground frame, position vector of this particle will be r, and position vector of the frame itself, the moving frame, origin of the moving frame from the ground frame is vector capital R, right? So let me write down here, this small r is position vector of P. P is the particle with respect to WRT, means with respect to capital X, Y, Z, that is ground frame. Now rho is position vector of P with respect to small x, y, z, that is the moving frame, and this r is position vector of origin of small x, y, z frame with respect to this capital X, Y, Z, that is with respect to the ground frame, right? So as if it's a car, I mean that swinging car also, so that the car moves in this way, and inside the car you observe some particle which is having position vector rho with respect to the car itself. However, so if these are the position vectors, their rate of change will give you velocities. So this, again let me draw this particle P, position vector from this rho, this is r, and this is the position vector capital R itself, and these are the frames. It's the ground frame X, Y, Z, and this is the moving frame, small x, y, z, and the small x, y, z is having angular velocity also. It is omega. So omega is angular velocity of the frame small x, y, z with respect to ground frame, obviously. Now this so velocity of the particle, velocity of P with respect to capital X, Y, Z, and velocity of P with respect to small x, y, z, and velocity of moving frame small x, y, z is, what is this? So these I these will denote by velocity of p with respect to capital XYZ, that you denote by v capital XYZ, and that will be equal to ddt of how much, ddt of r, and every derivative, you know, it depends on which frame. We are differentiating r with respect to time from the frame capital XYZ. Okay, now this is velocity of p with respect to small xyz, so that's v small xyz, relative velocity of p with respect to the moving frame. So that's d rho dt with respect to, obviously you are differentiating with respect to the small xyz frame. And by the way, velocity of the moving frame small xyz frame is r dot, and that's actually dr dt from capital XYZ. Okay, so don't confuse this. This is differentiating from which frame it matters. That's the thing. So that's for small xyz. This is from capital XYZ. This is from capital XYZ. Okay. So now they are from triangle law of vectors. We can write small r equal to capital R plus rho. Yes, this expression, and I'll in the next page I'll differentiate this with respect to time. That is not enough. Differentiating this expression with respect to time from capital XYZ frame. Let's go ahead. Small r equal to capital R plus rho. So we will differentiate it with respect to capital XYZ. See, differentiate it with respect to capital XYZ. Differentiate it with respect to capital XYZ. Okay. Now, what is this term equal to? This is V capital XYZ as I have described in the last page, and this is actually r dot plus, now this ddt of rho from capital XYZ frame is this. Again we can use that formula, you know. Which formula we'll use? Now we will use this formula, say a dA dt with respect to capital XYZ is equal to dA dt with respect to small xyz plus omega cross a. This was the formula if the angular velocity is omega for the small xyz frame. So here also we can write this, rho will be in place of a, so d rho dt capital XYZ is d rho dt small xyz plus this omega cross rho. Okay, let's put it again. Here v capital XYZ is v small xyz plus just this would have come before, omega cross rho plus, say, this term. I missed out this one, right? So that is it, right? This d rho dt small xyz is this term, v small xyz. So that is the expression for relative velocity. This one. Expression of relative velocity. Let's write it down again. A very small example I'll show you, and later on in a later video I'll give many worked out problems, so don't worry about that. So just this vxyz, velocity of p from ground frame, v small xyz, velocity of p from moving frame, plus omega cross rho plus r dot. So suppose one person is standing here, ground frame, and this is a moving frame, I mean not rotating, it's just a moving frame, this small xyz, and suppose a car is moving with a velocity v, right, velocity v from this with respect to ground, then obviously v capital xyz is equal to v, here all are in the x axis, so we won't write the vector signs actually, vxy, and there is no rotation also, so this term is 0, so this is simply vxyz is v equal to v small xyz plus r dot, so this r dot, this term r dot vector, right, so if you write this r dot is equal to u, so u, therefore that is a simple expression for relative velocity, that v small xyz equal to v minus u. This is a simple one, that is you are moving with a speed u and the car is moving with a speed v, with respect to this person, car will move with a velocity v minus u. And another very simple example I'll take, suppose there is a rotating turntable, looking from the top view, a rotating turntable, simple, this is fixed axis, and omega is the angular velocity of this turntable, and say this point P, and this, suppose the radius is r, so someone standing on ground, this is the ground frame, right, so what is the velocity of P from ground frame? Okay, so there is the frame x, say, suppose z axis on the top, so that is x, y, and say this is also small x and small y. Suppose this small xyz is rotating frame, small xyz is the rotating frame, so therefore v small xyz is equal to how much? Velocity of this particle p with respect to small xyz frame is 0, obviously 0, because if someone standing on this frame, for someone standing on this rotating frame, this particle p will be stationary, this p is fixed on the circumference, right, as p is fixed on circumference of the disk, right, so therefore we will use that expression vxyz, what was it, equal to r dot plus v small xyz plus omega cross rho. So here this is 0, r dot is 0, because this is not moving, this axis is not translating, it's fixed axis, it's a fixed turntable, so v small xyz is also 0, because with respect to a frame which is rotating with this turntable, that means after a certain time, when this particle moves here, this set of axes will also move, x and y will also, whatever this, this x axis and y axis, this axis will also move, right, that means this is a pair of axes on the rotating turntable, as the table rotates, this x and y axis also, and the z axis also on top. That's small x, small y, small z. This axis also rotate. So from the turntable you see it's static. Okay, so omega cross rho. So omega vector is this way and rho vector is this way. So omega cross rho means here it is as it is 90-degree angle, right, between this is a rho vector towards this from center to the point B, and omega vector, so omega cross rho will be this way, and this angle is 90-degree, so it's rho omega. This is rho omega. So therefore V small V capital XYZ is rho omega, omega rho, which in this direction. That is quite easy. Okay, you can also look at a pure rolling thing like this. Suppose this one. So this velocity of the center of this disk is V. Velocity of center of disk is V, and it's pure rolling. Pure rolling. So angular velocity is V divided by R if R is a radius. Okay, so you have to suppose this point is C and say this point is P. So at this moment this point is vertically above C. So from ground frame, so this is a ground frame. Okay, so to suppose V capital XYZ is velocity of P with respect to ground frame. So we will fix a set of axes with this, say this x and y, small x and small y, and small z is here, and so as this ring rotates, this axis also rotates. That means this suppose a ring rotates here, there this xy axis also rotates with the ring with the same angular velocity omega. That means my target is to see this point P fixed with respect to this rotating frame. So small x, y, z is rotating frame. It's translating also, right? Remember this from the ground frame, this position vector is r. So r dot is equal to v. However, we will deal with that later. So this is the rotating frame. Angular velocity is this way. Vector angular velocity omega is this way. Okay. So what do we have? V capital XYZ, that is velocity of P with respect to ground, is equal to V small xyz plus r dot plus omega cross rho, right? So what is V xyz here? V small xyz. From this small xyz, this point will be stationary because I've chosen a rotating frame, right? R dot will be u. Achha, let's put this vector u I cap. So this is the x axis, right? So u I cap, or you can write simply u also towards the right, and this omega cross rho is how much? This, I mean omega is towards, I mean into the plane of the paper, and rho is there, so omega cross rho is this way. So rho omega, so this will be rho omega, right? This value will be rho omega towards the right. So this is towards the right, this is towards the right. So this Vxyz is u plus rho omega towards the right. So this is actually a new way of finding out velocity of different points on this body, rotating body. You may solve it by different methods also, but this is one more way because we have used the concept of rotating frame.